بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. In this video, we're going to solve this exercise. And in this exercise, we need to solve a problem associated with plane wave incidence on an oblique angle, or oblique plane wave incidence. But the polarization that we're actually discussing is the perpendicular polarization. But before actually doing this, so let's just quickly go over perpendicular polarization. So the situation that we have an interface between two media, medium 1 and medium 2. In this case, we're assuming both medium 1 and medium 2 are actually lossless, but the analysis can be easily generalized when we have a lossy medium. So the wave factor, the incident wave factor, is simply given by this formula. So K1, which is omega square root of mu1 epsilon 1, multiplied by x sine of theta incidence plus z cosine of theta incidence. And the reflected wave, or the reflected wave factor, is similar to the incident wave factor, both in medium 1, but with a slight difference here in the direction of the wave propagation along the z-axis. So it's going to propagate towards the negative z direction. Similarly, for medium 2, we have the transmitted wave factor, but the key difference here is that the angle is simply the transmitted angle, not the incidence angle, and cosine theta t. So K1 is simply omega mu1 epsilon 1. K2 is omega mu2 epsilon 2. Okay. So at the interface, we have incident wave and reflected wave. We're considering the perpendicular polarization, or in other words, called the S polarization. So the electric field in this case is perpendicular to the plane of incidence. So the plane of incidence is the plane that contains the wave factor, this one, and the normal to the direction. Clearly here the plane of incidence is simply xz plane. So the electric field in this case along the y direction. So we found the expressions for in the previous class, we found the expressions for the electric field and the expression for the magnetic field. In this case, the magnetic field will have components along the x and z directions. And at the end of the day, we related the amplitude of the incident wave to the amplitude of the reflected wave using something called Fresnel coefficients. So the transmission coefficient is eta cosine theta incidence, eta 2 cosine theta incidence, eta 1 cosine theta transmitted, divided by their summation. The transmission coefficient tau is simply 2 eta 2 cosine theta incidence divided by eta 2 cosine theta incidence plus eta 1 cosine theta transmitted. And using Snell's law, we know that the angle of incidence is equal to the angle of reflection, and the K1 sine theta incidence is equal to K2 sine theta transmitted. And in this case, we define a new quantity called the refractive index, N1 sine of theta incidence equals to N2 sine of theta transmitted. So N1 is simply mu1 epsilon 1 mu relative 1, epsilon relative 1, and N2 is a mu epsilon, a mu relative 2, epsilon relative 2. So this is just a quick summary to what we did in the previous class. So now let's actually solve this problem. We have plane wave. This plane wave is radiated by an antenna that's very far from the point of observation. So we can assume that the wave that's emanating from the antenna is a plane wave. And it's at the interface between two media. So medium 1 is simply air. Medium 2 is soil at z equals to 0. We know the incidence electric field, and we want to actually compute the wave vector in medium 1, or before that, we want to compute, yes, the wave vector in medium 1 and medium 2 and the angle of incidence. So the first step that we need to do is actually we need to sketch the problem. So let's actually use, let's simply sketch the problem. So this is the x plane, the xd plane. So this is the plane of incidence. We have transmitted electric field or incident electric field. We have reflected electric field, and they have to be, this is theta I, this is theta R, and we have transmitted electric field. So epsilon R is simply, epsilon R is 1 here. It's non-magnetic, so mu R is 1. Epsilon R2 here is given, which is 4. So it's going to be 4. Mu epsilon R2 is simply 1. So since the wave is propagating from a less dense medium to a dense medium, so we expect that the angle of incidence is something like this. It's very close to the z direction. The angle of reflection, the angle of transmission is very close to the z direction. So this is in general the problem that we have. So let's solve the first part, which is determining K1, K2, and the angle of incidence. So first of all, we know that K1 is nothing but the magnitude of the wave vector on medium 1. So what is the wave vector on medium 1? So let's try to find this one. So the wave vector on medium 1, let's look at the expression of the electric field. So it has a z component, it has an x component. The value associated with x component is pi. It has a z component. The value associated with the z component is 1.73 pi. So this means that the wave vector of medium 1 will be x pi plus z 1.73 pi. Okay. The position factor, even though we don't need actually to compute it, is simply the general position factor x plus y plus z. Okay, so let's go back to k, the vector. So its magnitude will be, you take the square root of pi squared plus 1.73 pi all squared, and this gives you 2 pi radians per meter. So the first part, K1, we determine. So let's determine K2. Well, we know for sure that one thing is fixed between medium 1 and medium 2, which is the frequency. Is the frequency given to us? No, it's not given to us. So let's compute the frequency. So we know that omega is nothing but K1 multiplied by the wave velocity. So medium 1 is air, so the wave velocity is the speed of light in vacuum. And K1 is 2 pi, which is the quantity that we computed, multiplied by 3 times 10 to the power 8. And this gives us 6 pi times 10 to the power 8 radians per second. Okay, in medium 2, we know that K2 is simply omega divided by the wave velocity. So the wave velocity in medium 2 is simply what? Is the speed of light in the vacuum divided by mu r epsilon r. So mu r in this case is 4, epsilon r is 1. So c divided by square root of 4, which means that c divided by 2, this gives us 1.5 times 10 to the power 8 meters per second. Okay, excellent. So K2, in this case, is simply omega, which is 6 pi times 10 to the power 8 divided by 1.5 times 10 to the power 8, and K2 is 4 pi radians per meter. So now we found K1, K2. The last thing that we need to compute is simply theta I. So to compute theta I, we know that the wave factor in medium 1 is simply x. Let's look at it here. Let me use different color. So this is the wave factor. This is the angle of incidence. This is the normal. So the x component is simply the magnitude of this one, this vector, which is k1, multiplied by the x component. This is the normal, which is z. The x is this one. It's simply k1 sine theta I plus z k1, the z component, or the z component in this case is simply k1 cosine of theta I. You don't need actually to memorize it. You can use the angular relation here to find the expression for the x and z components. Okay, we know that k1 sine theta I equals to pi. This is what we have in here. Therefore, K1, which is what we computed 2 pi sine theta I equals to pi, which gives us sine theta I equals to 1 over 2. Theta I will be pi over 6 or 30 degrees. Pi over 5 or 30 degrees. Okay, so we're done with the first part. The second part is we want to obtain the expression for the total electric fields in air and in solid. Basically, what we want to do is we want to find the total electric field in medium 1, which is air, which is the incident plus the reflected. Okay. So what is the incident electric field? It's given to us in the problem. So the incident electric field is nothing but, so let me write it in the phasor form, y hat 100 e to the power minus j pi x plus 1.73 pi. We know that the angle of incidence is equal to the angle of reflection. So the reflected electric field is nothing but the incident electric field multiplied by the reflection coefficient e to the power minus j pi x minus, and be careful here, it's minus 1.73 pi c. Okay. So clearly we need to compute the reflection coefficient. And the reflection coefficient is simply N1. N1 here is the refractive index. And remember, we are able to use this formula because the material or medium 1 and medium 2 are non-magnetic medium, meaning that epsilon r in both media is simply 1. Okay. So we know N1, we know N2, we know the angle of incidence. The only missing part is simply the angle of the reflection angle. So let's compute theta t. So N1, square root of 1, which is 1. N2, the square root of 4, which is 2. And from Snell's law, we know that N1 sine theta I equals to N2 sine theta t. So 1 theta I is nothing but the quantity that we computed here, sine of theta I, which is this one, 1/2. And 2 is 2 sine theta t. This gives us 1/4 equals to sine theta t. And in this case, theta t is simply 14.5 degrees. If we take the value of theta t, plug it into this formula, we will end up with a reflection coefficient that's equal to minus 0.38. While we are actually computing the reflection coefficient, let's compute the transmission coefficient. We can either use the formula 2 eta 1 to eta 2 multiplied by cosine theta I, or we can actually use this simple relation. The reflection coefficient is simply 1 over the transmission coefficient, and this gives you 0.62 multiplied by, which gives you 0.62 simply. Therefore, the incident electric field is simply 100 multiplied by the reflection coefficient, multiplied with its sign as well. So the reflection coefficient is minus 0.38. So 100 multiplied by minus 0.38 is going to give you minus 38 e to the power minus j pi x minus 1.73 pi, and the unit is volts per meter. So let's compute the transmitted, or let's compute the total wave in medium 1 will be E total simply the real part. And I just want to point something out here, that the total electric field is function of x, z, and t. We're not considering the phasor form. So it's simply the real part of the incident electric field plus the reflected electric field e to the power j omega t. And if you do that, you will end up with 100 cosine x pi times 10 to the power 8 t minus pi x minus 1.73 pi z minus 38 cosine of 6 pi times 10 to the power 8t minus pi x plus 1.73 pi z. The unit is volt per meter. In medium 2, we have only the transmitted wave, which is you take the transmission coefficient, you multiply it by the incident field. So the transmission coefficient is 0.62 multiplied by 100. So this gives you 62. Now you have to be careful here because you need to adjust the wave vector to be K1 to be K2 multiplied by cosine theta t multiplied by sine theta t. This gives you pi. This is the x component. The y component will, the z component will be K2 multiplied by cosine theta t, which is 2.78 pi c. The unit is volt per meter. And maybe it's better to write it in this form so you guys will not miss it. So K2 is simply K2 multiplied by x sine theta t plus z cosine theta t. And if you do that, you will get pi. K2 is 4 pi, so you get pi x plus z 3.78 pi c. Okay, so let's write the time domain form of the electromagnetic wave or the electric field in medium 2. This is x, z, t, which is y 62 cosine of the frequency is fixed, so 6 pi times 10 to the power 8 t minus pi x minus 3.78 pi t. The unit is volt per meter. So now we're done with the second part. The last part is we want to determine the average power density carried by the wave traveling in the soil. So in this case, we can, in the soil is medium 2. So the average power traveling, well, the average power carried by the wave is simply the average power of the traveling wave in medium 2. Let me just add another slide. So the wave or the Poynting vector in medium 2 is simply 1/2. Well, here I want to find the average power. I don't care about the direction. So the average power, I need to take the magnitude. So the magnitude of the electric field is 62 squared divided by 82. 82 is nothing but 2. 82 is 60 pi. So this gives me 10 watts per meter squared. Okay, this actually solves this exercise. Thank you all.